Hello everyone, welcome back. I'm going to talk about section 2.4 in this video. So 2.4, the main point that you're going to get out of this lesson is talking about scatter plots. So scatter plots are when we go do an experiment, we kind of collect some data on some points X and Y, right? So it could be anything that you're going to see. If I modify this, if I modify whatever this variable is, do I get any change in this variable? Okay. So for instance, if I did something like I put in some fertilizer, we did like a teaspoon of fertilizer, and then I measured the growth, the corresponding growth in plants. So I set up an experiment where I have several plants, add different amounts of fertilizer, and I measure the corresponding growth from each one of these things. So I might have like 1 teaspoon, I get an inch of growth, 2 teaspoons, I might get 1.5, 3, like 1.9, 4, I might get 1.7. So there's some variability in here, but I would like to know if changing this, if I change the independent variable, this is the independent, do I get any change in the dependent variable? Okay. So the way that I kind of start working on this is that I want to generate a scatter plot. Okay, and that's just a picture that I can look at and kind of put this in graphic format and, analyze the behavior. Okay, so that's my slides that I'm going to go through, and then we'll kind of jump back over here and talk about some different things as we go. So here, this is a scatter plot, shows the relationship between two sets of data. So I've got one thing down here, and I'm usually doing, I'm kind of considering this as an independent, this is a dependent, but it doesn't really matter in this case. It is like, are these two things related? Okay. If a person's weight, if they weigh more, is the height more? So they plotted these things. So they just put the point, here's their weight. So they find their weight, find their height along here. The weight tells you how far along this direction, and then the height is how high up. And they just plotted these, several points based upon some survey. Okay. Here's another one. This is birth rate versus income. So this is kind of an interesting take, and it kind of shows in if you take any sociology courses. The birth rate tends to be lower in richer countries. So this is yearly production per person. This is kind of like, their income is kind of related, per capita person type thing. But here's the birth rate, 5.7, so 5.7 births per average person in Madagascar, where there's a low standard of living. And then as we go to the richer companies, this thing tends to reduce, go down. And just better education, they tend to, we have a better future. Let's control our birth rate, have methods to do that. Okay, so if we plotted all of these things, this is about 100 different countries that they went through here and plotted these things out. Okay, and the points are the scatter plot. Now, if you're just looking at this, you're just kind of having to make sense of it on your own. But you notice this line through here, where if I started over here and go all the way down and kind of get the middle of the data as we go through, the middle here, and kind of draw a line. This is called a trend line. So it shows you the trend of the data as you increase here. This is the birth rate along here. The birth rate tended to decrease as we increased 1. So the first thing we're going to do is kind of look at the scatter plot and then see if there is some kind of trend line, that there is a trend. Later on, we're going to talk about, well, maybe there's no trend. What does that look like? So the local ice cream shop keeps track of how much ice cream they sell versus the noon temperature on that day. Here are their figures for the last 12 days. So this is at a particular time when they've got some temperature, and here's the ice cream sales that they do. Okay, so just looking at the data itself, it's kind of hard to go through because I've got different temperatures, different amount of sales. different days, there's some variability in the temperature, variability in the ice cream sales. So we would like to go over here and put this thing in a plot, some type of scatter plot, and just see if there's something there that if one increases, in general, does the other increases. Okay. So here's the scatter plot. Some of these things are grouped together, and this may be at different days, but it tells you that as the temperatures increases, if I'm starting here and then I'm going up, if I go this way, these sales amounts tend to go up. Okay. So I could add a trend line, and what would the trend line look like? I would try to get through the middle of this, all the data. In fact, the trend line, the line of best fit, is actually mathematically found by analyzing all of these points, and it's a big formula to go through, a big process. But Excel does it really nicely. It just says, you click on the point, say add the trend line, and you get all of that data in there. So we did that in class. So here's the trend line that, either Excel or some other software package is generated based on that. Okay, and then it drew it through the middle. But notice what the trend line does. It attempts to minimize the error. So this trend line has an associated model formula for it, a straight line y is equal to mx plus b that we looked in last section. And it tries to get the difference between so you would use this as prediction. Like if I look here, if I use that equation of the straight line for 22, I would get pretty close to right on that one. But sometimes I'm off of these. But what it tries to do is say, this is the error. It was above. So we predicted on the line as prediction, we predicted above, here's below, and it tries to even out the belows and above to give you a minimum error. May not be zero because just the way the data comes, but it tries to minimize what the error would be. So here's a scatter plot of sea level rise. And if we kind of look at it and try to interpret it, I see 1993 up to 2011. So this data goes through that time period. And here's some sea level rise variability in here naturally because of tidal actions, different things. But as the time has gone on from 1993 to 2011, we see that the mean sea level has risen, over from a minus 20 somewhere along in here up to positive 30, 40 millimeters. Okay. So if we try to do a trend line, a line of best fit would try to minimize, go through the center of all of this data where the errors of the positives and the positive errors, the negative errors would minimize that and make it a best fit type of line. This is your best. Out of all the other lines, one down below, one above, out of all the possible lines, this one is hopefully the line of best fit. It minimizes the error. So once we do this, we've got our data over here. We go through, we build a scatter plot. Now we added the trend line first, but we go through here. I get some data, different points, different things, different times. But I get some general thing and I look at it. My first job is to build a scatter plot. And I say, I think there is something there. If I just see just a bunch of blob of points, looks like a big circle, just a big cloud up there, I'm not really going to go forward. If I think there's something there, and I might want to do this just to say here there is nothing there, I'm going to calculate this thing called the correlation coefficient. The correlation coefficient. The correlation coefficient, it can be calculated, by several software packages. Excel does it fine. TI-84, you can get it from the TI-84, the TI-36. Okay, but it is this value R. Okay, and it lies between -1 and +1. That's the smallest it gets, that's the biggest it gets. But what it tells you is how good there is, or how strong the correlation is between if I increase one, if one changes, how does the other change? Does it kind of mandate a change in the other thing? So here is the pictures of where we're going to go through, and I'm going to use this one. Let me start with this one because I like going left to right. -1 would be if I increased one data. If one data actually increases, the other one goes down. Okay? If one goes up, the other one goes down. If this one goes up, the other one goes down. The corresponding goes down. This one, if I did a trend line here, I would have a perfect straight line. All of these data points would lie along that straight line. That would be a correlation coefficient of -1. And then we kind of move out from there. Well, it's not, there's kind of a little bit of variation between this thing, but as I go, it tends to decrease the other one. So one increases, the other one decreases, but it's not along a straight line, but it's still clustered around some line. I would still get a good strong trend line there. Now, once I get down to like -0.5, this is pretty low. It looks starting to look like a cloud. And I'm saying, I don't know if there's anything out there, but if this is low here, this seems to be higher than when it's out here high. So I would run my correlation coefficient and I would get a -0.5 on that. If I could did a trend line, it would maybe be a useful model, but I would use it with a grain of salt. Okay. Here is no correlation. R value, this R value right in the middle of equal to 0, there is no correlation between one data set and the other data set. Okay. So if I walked around the cornfield and measured the growth, if I increase, one cornfield I walked around twice, one cornfield I walked around 4 times, 6 times, measured the growth, this is kind of what I would get. It didn't matter what I did walking around the cornfield, it's not going to tremendously affect the growth. And then as we move over here to positives, that just means that as we increase one, the other one tends to increase as well. Now this is a weak, low positive correlation. One increases the other, that's the positive. I could do a trend line here, but I would use it with a grain of salt. Here, this actually starts to look like I can do some pretty good predictions in here. This is the 0.9, and then a perfect +1, everything lies along a straight line. It's all in there. There's no error between what the trend line would be and these points that would be prediction. Okay, here only works well, the correlation calculation only works well for relationships that follow a straight line. Now, here, if we did back on this, here's the sales and the temperature. We only had a limited amount of temperature, a limited amount of sales. We could do a straight line through here, and we would do this as a pretty good model of predicting along this range, what we get. Okay, but now as we go down here, it says, look, we're going to go all the way up to here. It starts out, but then it starts going. It says, okay, probably people, it's just too hot to get out, so they're not going to go and start getting any ice cream sales. This fails to be a linear. You would have to do a different model to do this. This would be a polynomial model. Yeah. So in this, you would say, okay, I see a correlation value of 0. So whoever built these slides said they worked it out, so I trust them. If I did, it just, over that range, there's just no correlation. However, it's just the model. You could say within this range, I could do a linear. Within this range, I could do a linear model, but it would be piecewise. I would have to use 2 separate equations when the temperatures were that big apart. So here is sunglasses sold in comparison to the ice cream sales. So when it was cool outside, low number of sales, and as we went up, the more ice cream sales we did, the more sunglasses they sold. Okay. So again, that looks like a straight line within reason, within whatever the range of the fundamental. Here's the temperatures. Here's the ice cream sales, here's the sunglasses. I could use a model between here to get to model what would it be if I had ice cream sales of a certain thing, then I would have this many sunglasses. Okay. So at times I can work backwards from here to get to here, the inverse problem. Okay. So that's kind of the basis of the things that we want to talk about, the scatter plot. We can build our own little trend line. There's some problems that we would work, and it would say, well, do an estimate, do an approximate trend line, an approximate line of best fit, go down here, these pick out some point along, maybe you could even use the 0 point if it looks like it's in here, but pick a middle point. This would be like your X1, Y1 point. Some of these points up here, but try to get the middle, something in the middle that's close to this line. That would be your X2, Y2. Then your slope that we talked about last time. We get the slope, and then we go y is equal to mx plus b. We know what this is. Let's say 2 from here. And then what we would do is pick one of these points and plug that in. So if this was, let's say this was out at 710, then we would turn around and say, okay, here's our y value, that's 10. 2 times 7, that would be the x point that it had to go through. What b would let it go through? So all these lines, there's several lines with slope 2. I mean, a whole family, right? There's just infinite number of lines that's going to have that slope. This, by saying I want it to go through that point and that slope, that'll give us the b, and that picks it. So in this case, this would be the 14 plus b, and then I would solve for b, minus 14, minus 14, so this would be minus 4 is equal to b. So just saying this would be something like y is equal to 2x minus 4. So I hope that helps, and I will see you in class.